Good morning. Welcome to the Essentium webinar. This is Blake Teipel. We're delighted to have everyone here today. Very excited to share with you guys how to print faster, build faster, unlock strength, speed, and scale using Essentium's high-speed extrusion platform. Welcome to our webinar. We're going to go ahead and get started out of respect for the time of those who've signed up and who've already entered the room. So our goals for today, as we go through our content, we're going to provide an overview for Essentium, who we are, what we're doing. We're going to talk a lot about high-speed extrusion, or as we call it, HSE. What does that stand for? What does that even mean? And what does it do? We want to make sure that as people leave the webinar today, there is nothing mysterious about our technology or what it means for you, your organization, and the solutions that it can provide. We're going to provide some real-life examples on use cases and cost savings. We're going to explain our reservation program and encourage you, if you're here today and you're interested in high-speed extrusion and solutions at scale using additive manufacturing, don't miss out on our reservation program. We have a few slots left for 3D printers in 2018. I'll explain what that means, and we encourage you today, do not miss out if high-speed extrusion is something that is of interest to you or your organization. And we're going to close with questions. We really are excited about today. We want this to be an interactive webinar, an interactive opportunity. However, we are designing the content today to where we go through all the slides, all the information, and then we're going to have an interactive session at the end. So if you have questions during the webinar, please email kendra.pulliam@essentium3d.com. So I'm going to take a second here, give you guys the time to look at that email address, write it down, type it into your browser, put it into your web solution. And again, that's kendra.pulliam@essentium3d.com. Please email your questions. We're going to compile those questions real time in the webinar. Take the time at the end to get to as many of those questions as we can. We're excited for the content today. We're appreciative of the audience interaction. We want it to be interactive, but we're going to get through all the content before we take questions. So with that, let's start with an overview of Essentium. Who is Essentium? Some of you on the attendee list, we already know. Some of you have met with us at trade shows or have seen our content, interacted with Essentium over the last couple of years, but many of you have not, so welcome. Welcome to all of the folks here today, those of you who know Essentium and those who do not. So for those of you who've never met Essentium before, who are we, what are we doing, and what are we doing now, perhaps, that might be different from what you've heard in the past? Fundamentally, Essentium is changing the way things are made at scale. So we are closing the loop between prototyping and production, providing materials that designers can trust on a 3D printer platform, which is itself an ecosystem solution that solves all the pain points that we can address at scale. So fundamentally, in the middle of their picture, you can see we actually manufacture filament from soup to nuts in College Station, Texas, and we are setting up production as well overseas with some of our partners in Europe. So later on this year and throughout 2019, we will have global production with a global supply chain that our customers can trust. If you're, for example, an automotive OEM with operations in the US or operations in Europe or operation in Asia Pacific markets, you'll be able to buy our materials technology distributed with our partners BASF on a global supply chain that you can trust. We also test all of our materials against injection molding, against a variety of other molding technologies in-house and independently, sent out to third-party vendors to validate the strength, mechanical property improvement, and functional difference that Essentium's materials offer relative to the competitive set. And lastly, on the right-hand side, you can see hardware. We don't just tinker, but we are ourselves builders. At the end of the day, Essentium is changing the way things are made at scale. We are builders, building for builders. That is who we are. So let's start out by addressing some of the so-called elephants in the room here about why people have not been able to engage with 3D printing at scale or industrial manufacturing in the additive sense. And some of those are listed here. So whether it's mechanical properties or a limited range of materials, unreliable machines, closed material platforms, or unfriendly certification processes, there are a variety of reasons which have prohibited industrial additive manufacturing from taking root at scale. Essentium is here to address all of these. We have taken a fundamental first principles approach on our material sets, our machine platform, and our business model to ensure our customers can participate with our products at scale and apply the solutions at numbers and quantities that previously have not made economic sense. So I keep using this word scale. I think it's worth it for us to spend a couple of minutes here unpacking scale and saying, what does that mean for us? And the key here is that scale is truly unlocked when there is a manufacturing process that has access to speed, provides parts with high strength, operates itself with a great degree of accuracy and reliability, and is now plugged into the Internet of Things or Industry 4.0. Additive manufacturing can unlock these, but has not been found previously outside of Essentium solutions. So our platform is an internet-connected platform, operates with the reliability for semiconductor machine tool manufacturing tools, a high degree of accuracy also birthed out of the semicon area, high strength delivered by Essentium's flash fuse materials and flash fuse technology, and at speeds not seen before in extrusion additive. When you combine all these together, you get scale. And I'll explain today what this means, how we're doing it, and what it could mean for your organization. Again, extrusion at scale. So what we're doing is we're closing the loop between the prototyping cycle and the production cycle. So even if you have functional parts, imagine this, and many of you online today have done this at great length. You have a functional prototype part, even delivered by additive manufacturing, but how then do you transfer that part production process from an additively manufactured part to a part that is manufactured using conventional methods? So far, it has been too cost prohibitive to manufacture the same part on traditional, on additive methods. And so you have to sort of transfer that technology and recertify the part, requalify the part, do a PPAP, pull the part all the way through its certification process and production process on a traditional method. With Essentium's high-speed extrusion platform, we're unlocking the ability to functionally prototype the part and go into production of the part at scales that might surprise you using the same platform, same materials, and same process. This delivers not only the speed improvements already having been seen in the prototyping cycle, but also the speed improvements necessary for organizations looking to dramatically improve their time to market on the NPI cycles of tomorrow. We do that by addressing the factory floor. Our printer is designed as a platform solution to optimize its footprint in the factory floor. It is automation friendly, automation ready. All of the hooks for automation are built into the machine. We allow our customers, therefore, to customize and provide the automation solution that they use inside their factories using today's methods with our machine. So in this way, we address the factory floor in a similar manner to how injection molders and CNC mills have already been built to interact with the automation technology solutions of today and tomorrow. So what this does is it supplements and offers an alternative to traditional methods. For example, CNC milling of plastic parts, or even metal parts in some applications, and injection molding. Obviously, injection molding is kind of a catch-all. There are a variety of molding techniques for today's plastic parts, everything from rotomolding to compression molding, injection molding, blow molding, and the rest. The tooling, jigs, fixtures, and work aids for those techniques can themselves be produced on the HSE platform, and in many cases, the part itself. So what this does is it supplements the existing install base of today's machines and equipment, and all of this is backed by a global supply chain that you can trust. So let's get into the nitty-gritty on high-speed extrusion. At the end of the day, high-speed extrusion from a speed and reliability standpoint is solved at scale by looking at this equation. On the left, you've got cost savings. On the right, you've got time savings. So production efficiency in dollars per kilogram plus the time saved in hours per kilogram. If you put those two pieces together, you get true scalability. It is not enough to provide cheaper materials. It is not enough to provide a faster machine. Both are necessary but insufficient conditions in order to solve the equation for scalability. Essentium's high-speed extrusion through our materials model, our business model, provides both. So the high-speed extrusion solution, our platform, is a twin IDEX head machine that is fully enclosed, provides an all-of-the-above heating solution for high strength, and delivers on scale, design freedom, time savings, and cost savings. So how do we do this? And what are some of the specs of the machine at hand? The high-speed extrusion is capable of producing printed parts while extruding at greater than 500 millimeters per second for many materials, all the way from polyesters to polyamides to a whole variety of materials there, and I'll get into that in a minute. And our motion speeds are greater than a meter per second. So basically imagine that you've got a pick-and-place robot or a high-speed Cartesian semiconductor robot coming right out of the semiconductor back-end assembly process and transplanting that into additive manufacturing. That's what we've done with our motion system. And we've combined that motion system with the flash fuse extrusion system, which makes the parts very, very strong. So we achieve injection molding strength using flash fuse. And I'll get to that in a minute for those of you who haven't heard of that before. The accuracy, we solve accuracy by providing a machine with closed loop, multi-axis servo control. We have not only closed loop control on X and Y and Z, we also have closed loop servo control on the heater axis and the extruder motor itself. So what this does is provides the ability for the machine to know where it is locationally and where it is supposed to be locationally, which provides certification friendly solutions for our partners, particularly in FDA environments and FAA environments. From a reliability standpoint, we have no belts, no pulleys, and only 7 moving parts in the entire machine. Again, this machine is constructed from the ground up, fresh, first principles approach to be the most reliable printing platform in the world, full stop. We have auto characterization then of certified materials by using the closed loop servo motor controls on the heater axis and on the extruder axis. For example, we can even auto characterize our materials and tell you, the customer, hey, there's a problem with the material batch, or there's a problem with the machine setting, or there's a problem with the electricity, by the way, because you're not supplying enough torque to the motor. We have the feedback that we can provide to our customers. So our customers know that the machine is producing the part to spec. And by the way, in many cases, our customers are interested in multiple machines. So if you have a machine serial number 1 and a machine serial number 12, you'd like to ensure that the parts coming off of machine 1 and machine 12 are the same. Our machine will actually tell you that. And by the way, let's take that analogy one step further. If you have a production plant in Michigan and a production plant in Japan, you'd like to be able to compare the data coming off the machines and the parts produced in Michigan, the parts produced in Japan, to make sure that those parts are the same. If you're running nylon in both places, for example, our machine will tell you if those parts are produced to spec in both locations. And that has been missing in additive to date. Let's talk about the build volume. As I mentioned, our machine is an IDEX head. It's also capable to be built or configured as a single head machine with an IDEX. So that stands for total, independent extruder setup. So the IDEX is true independent head. The X and the Y are totally separate, meaning that you can build collaboratively on the same part. You can build separately 2 different parts using the tandem build configuration, or you can use different materials, for example, support material and model material, or hard material and elastomeric soft material like a TPU, all in the same machine on an IDEX configured machine. And it's a fairly large build volume. As you can see in X, Y, and Z, we're 725 by 530 by 600 millimeters. This provides a useful platform which can fit a wide variety of manufactured parts, including jigs, fixtures, tools, work aids, and many functional parts in biomedical, aerospace, and the automotive sectors in particular. We have a heated chamber much greater than 120 C. We are excited to be able to share with our customers today that our machine is going to provide the highest continuous operating temperature of any extrusion additive machine in the market. We also have an all of the above heating approach where we use our flash fuse technology and a multi-scale thermodynamics approach to really solve the problem of temperature in the polymer in the machine. This provides in situ stress relief, in situ annealing, and a lot of solutions for our customers. Our G-code. Let's talk about G-code for a minute. I mentioned earlier about how in some cases 3D printer platforms had been closed model, or the business models themselves have been closed model. Our platform can handle G-code on any Marlin compatible slicing program. So if you're running Simplify 3D, if you're running Cura, or if you're running a variety of other slicing solutions that produce G-code that is run on Marlin, style machines, our machine can interact with that G-code and produce the part. If, however, you are running a more sophisticated G-code with FANUC extensions, let's say G2 through G6, including splines, NURBS, and other common FANUC extensions for CNC mills, our machine can also handle the more sophisticated G-code, which itself speeds up part production. And lastly, but not least, our machine has a built-in filament dryer with automatic despooling and filament changeover so that our spools and our materials are taken care of from the moment they hit your factory floor to the moment that that part is produced. Let's talk for a minute about strength and flash fuse technology. As many of you know, Essentium got our start addressing the interlayer delamination issue with fatigue and impact loading for 3D printed parts. And so as we started this process, we basically figured out a technique to address the interlayer delamination issue for 3D printed parts so that we do not have parts that delaminate in Z like FDM does. So the way we've addressed that is by using a multi-layered filament that has a carbon nanotube composite coating. So you have carbon nanotubes fully encased in a polymer master batch that we apply in production. The filament itself is a multi-layered filament. That's what makes Essentium's flash fuse filament, or Essentium Z, UltraFuse Z, a different filament than other filament available on the market. While the part is being printed, we hit that part with electromagnetic energy in the form of high energy plasma so that the polymer chains in between the layers have sufficient time at temperature to heat and cross the layer boundary, fully entangling. This provides Z strength that is on par with the X and Y strength. That has been missing an additive without Essentium's technology. So what does that look like? Well, here's a video of the plasma in the printer printing the parts. So you can see there's two devices under build. This is a tandem build. This particular video has been slowed down to about 35 millimeters per second. We're building the part, we're heat treating the part as it's being built. So what does this provide from a data standpoint? Statistically, our flash fuse ZX tensile strength data is on par with the tensile strength data for injection molded materials. Now, this is a polyamide material produced with our friends and colleagues at BASF. It's been, checked and looked at by them, by us, by others, and we're excited to provide this to the market in 2018. As you can see, the third bar on the right, that's the ZX strength for polyamide material that is typically seen in fused filament fabrication, or FDM type processes. All right, so let's talk about the materials roadmap. Which materials will be available in HSE? As you look to the left of the slide, you see the polymer pyramid. Many of you on this webinar today are familiar with the polymer pyramid. It's basically separated by usage temperature and operating temperature. So you have 100C, 150C, 200C, different usage temperatures on the polymer pyramid. You have amorphous polymers, semi-crystalline polymers. We are providing a range of release materials at the time our printer is released, greater than 20 materials before the end of the year that are HSE certified. This includes materials that have been developed and co-developed in collaboration with BASF and others. So you have polyamides, you have polycarbonates, ASAs, TPUs, PCTGs, also metal, by the way. We're excited to announce that the BASF UltraFuse 316 stainless steel will be available in extruded filament form on our HSE platforms. Also high temperature materials such as PEEK and ULTEM. And then you have a variety of those materials over on the far right-hand side of your screen that are multi-layered filaments. So everything in the blue box, that is a multi-layered filament product. So everything from polyamide down through ULTEM will be available in the so-called Essentium Z brand, which is both Z strength improved and ESD safe. And ESD, by the way, is going to be a whole other webinar, so stay tuned for that one. So I'm just going to take a brief pause here and before we launch into the commercial side. And what we've done so far in the webinar is we've explained what HSE is. We've explained what flash fuse is, how that translates into speed improvements and strength improvements for your organization for the printed parts themselves. We have not yet discussed the actual commercial side. That's what we're about to get into. I'll provide several use cases on that, but I just want to remind the audience today, if you have questions during the webinar, please email Kendra Pulliam. That's at kendra.pulliam@essentium3d.com. And we are compiling questions real time through this webinar, and we will answer as many of those as we can get to at the very end. So please don't forget, email us your questions. Everything from how does the platform work, to is this material going to be included, to what does IDEX twin head technology mean, to how much does it cost? Any of those. We'll get to that, but we'll take those questions at the end. So let's provide a couple of use case informations. We have some injection mold tooling use cases for automotive, aerospace, consumer goods, electronics, and the rest. So I'm going to highlight a use case here. First of all, we started out by providing a preform for injection molding where we 3D printed using a carbon fiber infused composite material. A carbon fiber infused composite. We 3D printed the preform as a 5 kilogram part, took about 75 hours to print. We have a 1 millimeter nozzle, 550 micron layer height, 100% infill. So a fully dense part, or as fully dense as you can get with FDM. But again, that is also a separate webinar. But this is a fully dense part, 5 kilograms. What we then did was we took the preform and put it onto a CNC mill, milled off the top layers to achieve a Class A finish. So we achieved a Class A finish on the insert using sort of traditional mill settings, and it was very rapid and very fast, and able to produce a high accuracy part. So we then took the insert, as you can see on the left-hand side of the screen, and inserted the insert into a large injection molding machine. It was a 450-ton machine. We ran the machine with coolant water, monitored the mold temp just like you would on an aluminum or soft tool, watched the mold temp, the skin temp, and the printed part temp as we ran through the injection mold parts themselves. And as you can see on the middle, we achieved over 100 parts that were injection molded on top of a 3D printed insert. And these parts, the material that was used here was a polypropylene with chopped glass fiber and talc. So this is a common, sort of commodity grade, high volume material set, and produced over 100 parts with a Class A finish on this material. And this material is an ultrafused polyamide carbon fiber material that was produced using flash fuse technology and using Essentium's manufacturing techniques, and we're excited to scale that out this year. So let's talk about the time saves if we were able to produce that on HSE, and we're looking forward to doing that here soon. The 3D print insert becomes the insert in the mold, and on typical FDM, as I mentioned, took us 75 hours. This was an open platform FDM running a polyamide carbon fiber composite material at sort of standard speeds. The standard speeds for that are about 50 to sort of 75 millimeter per second print speed, 550 micron layer height, as I mentioned, 1 millimeter nozzle. Using all of those same settings, running on the HSE, which has our high-speed motion system combined with our high-speed extrusion system, you can experience nearly a 10x time save on that printed part. So not only are we experiencing time save to produce the soft tool using additive and going from sort of multi-weeks down to a single week with FDM, then when you produce the part itself on HSE, you're going from a single week to a single day. So the time save, again, is quite usable and it's quite dramatic. Let's talk about cost saves. So how does HSE save your organization money? So we analyzed a couple of different parts, and I'm going to walk you through two different case studies now where we compared HSE to Ultimaker's, a Fortis, and a Markforged X. So we analyzed this material. So on the left-hand side here, you basically have the HSE 180. We used a nylon material for all of these analyses. We used a 1.2 millimeter nozzle in every case except for the Markforged X. And we are showing our material price strategy here, where our material pricing is, again, priced at a point where it competes with sort of, economic models that make sense. This was a 920 gram part, so fairly large, bulky part. On HSE, that time to first part would be less than 3 hours, 2.9 hours. The cost, all in landed cost, machine, material, maintenance, depreciation, landed cost on that part is $78. So what that provides for your organization is a dramatic time save and a dramatic cost save. And you can see how we did the setup there below. Again, 1.2 millimeter nozzle, 600 micron layer, 33% infill. And I think you can see kind of the rest there. So again, I just want to highlight the time save is dramatic for this part. The cost save is also dramatic for the part. And this is the cost for the landed part. We're not even factoring in the true cost save from the actual hours, themselves, because as you can imagine, that would be difficult to model for different organizations. Let's look at a smaller part. So it's all well and good to say, well, I've got a lot of large chunky parts, so that's going to be a nice time save. Let's look at some small parts though. This one was an ESD fixture. So ESD is, again, electrostatically dissipative fixture. So the fixture's got to absorb electrical energy and electrostatic shock. And our materials do that. Essentium Z and Ultrafuse Z materials do that. Printed on a 0.4 millimeter nozzle for a high degree of part accuracy, $70 per kilogram part. This is an 11 gram part, and it takes 0.14 hours and provides a cost of only $1.96 for that cost, for that part itself. So again, you can see how we've set that up. This is an ESD nylon, 0.4 millimeter nozzle, 10 micron layer height, 33% infill, fairly standard settings for kicking a part out, getting the accuracy and the feature size you need, high strength part, not, full functional in terms of like tensile strength and Z, but high strength, fully functional part for production. But what if your monthly usage is 1,000 units or even more than that? Well, what we did is we analyzed unit economics for the cost of, for example, fixtures, although insert any other, functional part there instead of fixtures. Doesn't have to be fixtures. We just looked at fixtures. Fixtures themselves in the semiconductor and PCB, markets have to be produced in lots of up to 1,000 fixtures. So we analyzed the total landed, fully burdened cost for that part on a 30-day run for a 2 kilogram part. So picture this, you've got 1 month to produce 25 parts. That's the problem. The boss comes to you and says, hey, I need 25 parts in a month, or I need 1,000 parts in a month. And as your job as a manufacturing engineer is to produce 25, 75, 350, or 1,000 of those parts and get them landed on the factory floor in the next month. How do you do it? If you've got injection molding or CNC assets at your disposal, you can of course use those, but those injection molders and CNC mills may be burdened manufacturing other parts. So it would be useful to have a technology set that did not burden your existing production assets. So that leaves you sort of with an additive manufacturing solution of either FDM or HSE. FDM simply becomes cost prohibitive as you scale. It has not had the cost breakthroughs that are needed in order to provide parts at scale. Now, imagine yourself that the boss said to you, hey, I actually need you to procure the capital equipment to produce these parts. What would that look like? Well, if you had to spend money to procure the capital equipment, the CapEx itself, let's take a look at that. Again, you've got 1 month to produce 25, 75, 350, or 1,000 2-kilogram parts. Okay, so these are the lot sizes that we're looking at here. If you had already the money to set aside for sort of injection molds, CNC, or FDM, you'd be spending around $250,000 for sort of a standard size machine. Of course, there's cheaper ones out there and there's more expensive ones out there. We look statistically at sort of a common, CNC mill, common injection molding solution, about $250,000. A single head HSE platform starts at $55,000. So there's the price point for many of you who are asking that question. Price point for a single head machine, $55,000. You could produce even 75 2-kilogram parts very easily on a single head machine, meaning if that was your lot size in a month, all you need is a single HSE platform to produce that part. Whereas, for example, given the print time limitations on, for example, an FDM platform, you would need 2 platforms in order to produce 75 2-kilogram parts in a month. Moving up to 350 and 1,000 parts per lot, you can see our fully landed, fully burdened, depreciated cost, $220,000 for HSE for a lot size of 350, $605,000, pardon me, for HSE for a lot size of 1,000. So there's clear examples there on how these solutions scale into larger lots. And if you guys are interested in more detail behind this analysis, please email us, contact us, let us know. I'd really like to learn more about how my particular use case could scale. Let us know. We'd love to work with you on that and answer those questions in greater detail. So let's talk, as we wind this thing down, let's talk about our reservation program. Currently, HSE is in late stage development. Our high-speed extrusion platform, HSE 180, it's in late stage development. We're running prototypes. These platforms have already been signed up to be produced and distributed to a handful of beta customers, and that is going on right now. So if you want to get your hands on this technology, how do you do it? What we're asking our customers to do is to sign up and reserve your spot in line. So we are currently taking reservations for our release of the limited number of platforms we have in 2018. And we're taking reservations for that. We have a few spots left, as I said. Now, I want to be clear, this reservation is non-binding. We ask that you pay a $500 fee to hold your place in line. If you decide that you are no longer interested in HSE at any time for any reason, you may get your money back and go on and buy somebody else's technology, no problem. We just want to make sure that if, for example, again, I come back to this, if you're a global automaker and you'd like to have an HSE platform in 2018, or even in this case, early 2019, you absolutely must reserve your place in line so that that printer has a name. And then our application engineers will work with you to develop your use case, configure the machine per the production requirements that you have in your organization, and we will go into the reservation status from there. So we really encourage you, if you're hearing my voice today, if you are in this webinar and you're asking yourself, does HSE make sense for me? Even if you don't yet know, I encourage you, reserve your place in line. We will work with you to answer the questions, does it make sense or not? If it doesn't make sense, you can drop out of the program at no penalty whatsoever. We will refund your reservation fee. You can go about your merry way, and we can talk next year or at some other time in the future when you're ready to see the parts for yourself. But if there's an inkling in your mind of how high-speed extrusion might be of interest to you, your colleagues, or your organization, and you want to sign up, you want to learn more, we will develop the applications with you, develop an understanding of what that is once you've reserved your spot in line. So I want to be clear, this opportunity is available for everybody. Go to essentium3d.com/reservation, put in your information, put down your spot in line. We will contact you. We will work with you with our application engineers to understand your use cases and your requirements. You can say, hey, I'd like a single head machine, or I'd like a twin head machine. I would like, single head flash fuse machine or twin head flash fuse machine. and we can work with you to configure the machine to your heart's content and to your organization's requirements. But we will have a tough time doing that if we do not know of your interest. So indicate your interest by reserving your spot in line. Thank you so much for your time today. We're about to go into Q&A and transition over to the spot in our program today at the webinar where we go through and answer your questions. And again, if you have a question, email kendra.pulliam@essentium3d.com and we will get to your questions. So I am starting to work through the questions now. And actually, while we're doing this, I'm going to sort of also flash this information as well. If you have additional information, you may also contact Josh Lawson to reserve your HSE. Visit essentium3d.com/reservation. Okay, I'm going to start in on some questions here. So we've got a question from the audience. Okay, so the first question is, are we planning on using machine monitoring to track the health of the machine itself? And then the follow-on to that is, in this way, we can ensure that the part build quality and the predictive maintenance are in hand. The answers to that are yes and yes. The machine will be able to monitor, provide machine health, provide time since last service, date, so operating time since last service, date of last service, and system serviced. We are providing service contracts as well with the sale of the HSE. The service contracts themselves are actually very, very cost effective because, as I mentioned, there's only 7 moving parts. So don't expect to see a huge cost for service contract. But when you sign up for that, you absolutely get the machine health, machine monitoring, and the ability for our technicians and our service folks to understand what the service requirements are for your platform. Okay, good question. Next question. All right, why wouldn't someone just use a bunch of desktop printers to achieve scale? Man, that is a fantastic question. That's something that we've actually done ourselves through our biomedical business. So one of the things that Essentium's done is we've already proven supply chain disruption using a biomedical business called Trifusion Devices. Some of you have heard of it, many of you haven't. Trifusion Devices, just for those of you who don't know, produces bespoke medical parts from a 3D scan, 3D print, 3D model workflow. And we have been using about 10 open platform desktop style FDM machines for the last 1.5 years to deliver bespoke printed parts all over the US. Let me tell you, it can be done. Is it a great solution for scale? Absolutely not. We are tracking and monitoring part to part variation, machine to machine variation. What's more, it takes about 10 printers, 10 FDM printers to equal the output of 1 HSE chassis. That's a single head HSE chassis, by the way. If you have a twin head HSE, you can print 2 different parts on the twin head at the same time, right? You're matching it in Z, you're monitoring it in Z, and you can add additional parts onto that build volume. You can stack parts, plate them, and you have that full optionality available to you using HSE. Those optionalities are not available using today's open platform desktop printers. So if you'd like to scale using open platform printers, absolutely that's an option to you. You will need more floor space, you will have part-to-part variation, and it will be a real challenge to monitor the machine maintenance and the material usage, the material consumption, and all of those related items if you use multiple machines versus a single HSE. And as I just showed, the use cases, a single HSE part can be produced at cost per part equivalents, which exceed the cost economics provided from a desktop printer such as an Ultimaker. So, if you're asking yourself, can a $55,000 machine make sense if I have a budget to buy a $3,500 machine? The answer is yes. The $55,000 machine can absolutely make sense if you're cross-shopping it with a desktop platform because your total landed amortized part cost is the same or better. Okay, a couple other questions. Resolution and tolerance of HSE. Yeah, great question. So the total all-in system resolution is right around 10 microns. So that's 0.01 millimeters. So the way we achieve that is this. We use all linear motors. Our linear motors use magnets, and the encoders themselves on the linear motion axes, X and Y, for example, we have 1 micron encoder resolution. So as with every mechanical system, there's tolerance stack up and there's sort of overshoot and undershoot in a mechatronic system. We can tune all of that out using feed forwards, look aheads in the software, so that when our machine is turning corners, when our machine is settling, we are tuning all of that settling out. Since we have servo motors, we're tuning the settling out. So that's how we handle it from a mechatronic standpoint. From an actual, positional accuracy standpoint, again, Linear encoders on X and Y are at 1 micron accuracy. Linear positional accuracy in Z is at about 10 micron. By the time you stack up all the tolerances and you stack up the positional accuracy across all 3 axes, we're right about 10 micron on the positional accuracy. So that's your positional accuracy piece. As everyone knows, with any extrusion process, there then enters the sort of, extrusion width, trace width, how square is it, how well does the extrusion line up. What I can tell you is our extrusion system uses a low thermal mass, rapidly heating and rapidly cooling extrusion system to where we can actually cool down the extruder very fast to eliminate things like over ooze, and material over extrusion, and address that in the print, which also provides a very accurate part. So to sum it up, our part accuracy is achieved by using a highly accurate motion system with really good closed loop servo tuning and feed forwards in the software, combined with an extrusion system that is a low thermal mass, rapidly heating nozzle solution, and also the sort of plasma system on HSE, which provides another tool set for the manufacturing engineer to actually tune the thermodynamics. So that's the actual solutions we have for the resolution and the tolerance of HSE. Okay, so there's some confusion. Okay, great question. So there's a little confusion about what materials are actually available to buy and print on HSE. Yeah, great question. So actually, to answer, well, I'm not going to flip back because it's going to be hard, but what I will tell you is that there will be greater than 20 materials available for print on HSE. The materials range from TPUs at 80 Shore hardness through the UltraFuse TPU portfolio, all the way up to PEEK, carbon fiber PEEK, Ultem, PESU. So just imagine, the material opportunity there from an elastomeric at an 80 Shore hardness all the way up through a high temperature PEEK. You have many materials available for you in that window. What we're working with our customers to understand is this. For example, I'm kind of coming back to automotive again. For example, there are some materials in automotive, let's say PCABS or some other material set for automotive like polypropylene, glass fiber filled polypropylene. There are some specific use cases for which we have specific grades of materials that are being asked. If you have a use case like that, let us know. If you need a custom material, let us know. Let's pretend, for example, that TPU is not great because of nonlinear viscoelastic response at low temperatures, and you want a TPS, a TPV, or a TPC, or a TPE, let us know. And we will release some material. If the use case justifies it, we will release some material for HSE that will be used and functional for your application. And in addition, I want to be clear, we have metals, at least 2 metals that are going across the platform and will be certified for HSE compliance as the platform is released. In 2019, we have at least an additional 10 materials that are in development now, which will be released and HSE certified as well on an ongoing basis. And we're never going to penalize a customer. If, let's say, for example, let's say PEC, I'm kind of honing in on PEC. Let's say customers are using PEEK, but let's say that we're working on PEC, for example. If PEC becomes released and it is HSE certified, we're never going to penalize customers for upgrading later to also running PEC. It's not going to be an additional cost to your organization. Okay, a couple other questions. These questions are great. Okay, another question here. Will our machine run other suppliers' standard filament? Yes, it will. That is a fantastic question. So what we believe in is that the future belongs to the customer. And in additive manufacturing, one of the things that has held back the adoption of additive across the industrial sector is that additive companies of the past have believed that the future is theirs. They have believed that the customer doesn't know what they're doing. We think that's silly and foolish, and we are actually resisting any type of closed business model. So what that means is our machine will be released with pre-certified material sets, HSE certified materials. And to be clear, some of the materials, due to the high-speed extrusion process, will process differently or more accurately or better on HSE than on an FDM platform. So FDM-capable materials will function on HSE, but not necessarily the reverse. Okay, I just want to be clear about that. But if you're running, for example, PLA or PETG, I mean, we don't have PETG in our portfolio. We have PCTG in our portfolio. We like it for a variety of reasons, but let's say you love PETG, you can absolutely run PETG on our platform. Do we certify the platform performance? No, we do not certify the platform performance on a non-Essentium material. However, will we penalize our customers or dock the warranty? No and no. You can run your material on our platform and develop the process to your heart's content. We just can't speak to how the printer will run in that case. You're going to have to figure that out for yourself, and we will help you do that to the best of our ability. We'll be focusing on releasing certified materials that are HSE certified that run on our platform, so that our customers who want a science project, as I mentioned, they can run their own material if they want a science project. But if our customers do not want a science project, they just want to go into production on a material they can trust, then that HSE certified material will be ready and available from Essentium. Okay, so let's talk about, okay, another question. Great. So I have a question about the difference between a single head and a twin head. So the twin head machine is two single head carbon copies of each other on the same sort of X tray, right? So the X tray runs sort of linearly left to right. And the reason why we have a difference in the X axis spec for a single versus an IDEX machine is because with an IDEX machine, you have two Y cars and two Y carriers installed, whereas with a single head machine, you only have the one. So for example, on the IDEX machine, I think it's 700 and some millimeters. On the single head machine, the total X linear width is much wider because you simply don't have that second head installed. Our machine architecture is designed for modularity. It is designed for to be scalable. Again, if there's a use case where you need taller Z or shorter Z or wider X or narrower X, come let us know. Let us know what your use case is, and we will talk to you about that. All right, so I hope that cleared up that question. If it didn't clear up the question, please feel free to ask. We've got a few more minutes, so please feel free to ask a follow-up question by email. Okay, is HSE, I got another question. Is HSE a subcategory of FDM? Oh, that's a great question. No, the answer is no. HSE is built on top of FDM, but it is a fundamentally different extrusion process. We are pushing the speeds, the extrusion speeds through the print head into regimes not yet seen or not previously seen in extrusion additive. The way we can do that is basically by building a high pressure system in the head that pushes the filament through and liquefies the filament in a dramatically more efficient way than has been done before in extrusion. So we have some new IP, some new process technology that we've invented that fundamentally separates HSE from FDM. When you look at the printed part coming out of HSE will most closely resemble the printed part coming out of FDM. If you just look at it, set the two parts side by side on the table, they will look similar. HSE is built on top of FDM. It is an extrusion-based technology, but it is a fundamentally different extrusion and different motion system technology. So I want to be clear about that. It's a fantastic question. Okay, a couple more questions. Are we developing software to compensate the shrink factors involved in the sintering of ultrafused material? Wow, what a great question. That's going to be the topic of another webinar. I'm excited to say that there's a lot of development going on with ultrafused metal materials such as the 316LX and upcoming materials put out by our partners at BASF. I can't really get into that today, but stay tuned. Okay, we're just getting through to the last question for the day. It's coming in right now, real time. Last question. Okay, is it possible to upgrade from a single head to a dual head? The answer is yes. You absolutely can upgrade. If, for example, a customer would like to procure a machine and start with a single head machine, test it out, understand the ROI, build the use case, the material set, and the application understanding, and then upgrade to a dual head, yes, that can absolutely be done. We can do that in the field. We can upgrade the head in the field. It'll take about a day. We'll send a service tech out, and that can be done on the machine in the field. So that's no problem. The machine's built to where the drivers, software hooks, firmware hooks are all set from the beginning to actually be exactly the same on single head and twin head machines. And then we just plug in basically the cables and the drivers between the single and the twin head. So it's built from the ground up again for a high degree of modularity. In fact, we've contemplated setups with as many as 4 heads. So some of you have seen the Escher products put out by Autodesk. That's really exciting. There's many heads. I think the ones that I saw had 4 heads that were independently working. We've contemplated that setup in our machine as well. For now, we're set with twin heads, but in the future, stay tuned. Okay, with that, I'm going to invite you guys to, again, sign up for HSE reservations. And again, That can be accomplished at essentium3d.com/reservation. If you have questions, email josh.lawson@essentium3d.com or kendra.pulliam@essentium3d.com. Thank you so much for your time today. Please get with us, contact us. We want to work with your organization to understand how HSE will be a dramatic time save, cost save, and economic advantage for you, your manufacturing partners, and for your supply chain. Thanks, and help us unlock additive at scale.